Today's lesson is terminology for linear relations. We've gone far enough in the chapter to get the basics of linear relations down pat. And so now we can expand our vocabulary, if you want, of all the little things, some of which you've already seen and some new things here. So I'll just start off this PowerPoint here. Again, the title is Terminology for Linear Relations. 11 slides, it said, so not too long here today. Quadrants, you may have seen this before. The Cartesian coordinate system is divided into 4 sections called quadrants. And the quadrants are numbered weirdly as follows. You might not be the choice you would make to number them. And the reason they're numbered the way they are is not quite clear in grade 9. They're numbered 1, 2, 3, 4 counterclockwise like that. It has to do with what's going to happen with angles and coordinates later in high school. In about grade 11, we'll start putting angles right on these quadrants, and when we do that, it's going to be most convenient to work off the x-axis counterclockwise so that we go right into the first positive quadrant there. Well, that's a short version of understanding why it's numbered this way. I don't want you to think there's no logic to this. There is a very sensible reason why we number them this way. For your purposes, if you have to mention the number of the quadrants, they're numbered this way: 1, 2, 3, 4. Relations. Now, a relation is a description of how two variables are related. Not a big surprise there. When we're talking about how two variables work together, we're talking about a relation, and that relation can appear in different ways. It can appear like in a word problem like this: the connection between the number of minutes you talk and the cost of your cell phone bill. That's an out-of-date example because that was back when cell phones, you actually had to pay by the minute that you used them. Nowadays, maybe you can think of the cost of the cell phone and the number of gigs of data you use, something like that. And then there's a relationship there between how many gigs of data you use and what the cost of your cell phone will be. We can also give relationships or relations in equation form, like we've seen, y equals 5x minus 9. That's the equation of a line that we've seen a bunch of times this chapter already. This particular line would have slope 5 and would have an y-intercept of negative 9. Or a start value on the y-axis. I've tried to sneak that other word in there for you because you're going to see that this section. So, and as I've mentioned, relations can be represented in many ways. When you've got a relation between two variables, we can make a graph. There's what's called a parabola. You'll see those in grade 10s. In grade 10, it's not a straight line like we've been doing. So we can get graphs. We can make a table of values. You would have called this maybe a T-chart in grade 8. And we can also get an equation, but also maybe the relation will be given in words like this. Rick starts with $4,500 in his savings account and deposits $250 every week. How lucky for Rick. Okay, so we got 4 basic ways. Not that there's not other ways to represent relations, but in math we'll generally use graphs, tables, equations, and the word problem. Those will be the 4 basic representations that we'll use for relations. Now, we're talking specifically this chapter about linear relations. And linear relation is a relation that creates the graph of a straight line. So when we go to graph it, we'll get a straight line. So let's take a look at a couple and just decide if they are a straight line or not. There's a graph straight from grade 12. We do a lot of study of these type of graphs in grade 12, but it's not linear. It's not a linear relation, so we won't do much with that in grade 9 at all. How about this one? Is it a straight line? Yes, that one's a straight line. That's more like what we're studying in grade 9, is linear relations. Oh, table of values. Now, with a table of values, it's not quite so easy to see if something's linear. And what we have to do is look at the y values and say, how much is the y value going up or down? Is it going up by the same amount every time? Because it's got to be going up by the same amount or down by the same amount every single time if it's going to be linear. We look and we go negative 15, negative 21, negative 27, negative 33, negative 39, negative 45. What's happening there? Oh, it's going by 6 every single time, down 6 every time. So if I went to graph it, I would get a linear relation because it's going up or down by the same amount every single time on the table. How about this one? Does this one go up by the same amount every time? It goes from 0 to 1, it goes up 1. Then it goes from 1 to 4, it goes up 3. I don't even have to check the rest of it. I can see it's not going up by the same amount every single time on the y value, and so that one's not a linear relation. A plumber charges an initial fee of $95 and an additional fee of $40 per hour of work. I just want to mention the reason plumbers charge like this is they charge you $95 just to come to your house, and you say, well, you didn't even do any work yet. Well, yeah, they did. They got ready, they loaded their truck up, they reserved time for you, they used gas money to get to your house, so we have to pay them for all that getting ready to be a plumber type stuff if we want them to work on stuff at our house. So the question though is this a linear relation? And even though his fee starts at 95, it's only going up by $40 each hour. Only. That's a big number, but it's going up by the same amount each hour, which means that this is a linear relation because it's going up by the same amount each time. We're really not trying to trick you in grade 9 too much, and this one could trick you. We're not intending to, but this one is weird. Let me read it and then talk about why it can trick you. Rita has a vintage guitar that is worth $16,400. Every year its value increases by 5% of its previous value. It's tempting when you first see that to say it's linear because it's going up by 5% each time. But because the value of the guitar is going to be changing, that 5% is actually going to be different every year. It's going to be 5% of a different amount. So as the guitar gets more valuable, that 5% of its value becomes a larger and larger number. And so it's not increasing at the same amount each year. So percentages are strange like that. They can sort of fool you because it says 5% every time. You might think that it's the same all the way up, but it's not, because the 5% isn't changing, but the 5%, the value is changing, so that how much it goes up changes every single time. Oh, y equals negative 5, 6 plus x plus 8. We're now at the point that hopefully when you see that, you know it's a linear relation. It's in the form y equals mx plus b. It's got some number in front of x and some number by itself. That number in front of x we called the rate originally. Then we started calling it the slope. That number by itself, the plus 8, we called the start value. Then we started calling it the start value on the y-axis. And soon we'll just call it the y-intercept. And yes, that's a linear relation. We've done enough work with those to recognize equations that are in y equals mx plus b form are linear relations. Independent and dependent. This is sort of difficult. I don't want you to, if by the time I'm done explaining, if you're like, okay, I sort of get it, that's maybe the best we can do for now, is to sort of get what independent and dependent is. You might go, oh, I totally get it already. Well, good. I hope you do, but it's just a little bit tricky to talk about independent and dependent. Independent variable. One way to think of independent variable is the variable you choose. It's the variable you decide on. You go, oh, what about for this value? The basic example I can use is, let's say you had a job and you were making $10 an hour. You would then choose how much you're going to work. I'm going to choose I work 8 hours. How much would I make? $80. So the independent variable is how much you sort of decide on. It's what you plug in to find the other value, the dependent variable. So this variable affects the other variable. Based on what you choose for your independent variable, you'll get different values for your dependent variable. So the dependent variable, it's the variable that you calculate. I'll say usually. That's where this is complicated. It's most often that what you're going to do is plug in an independent variable number and get a dependent variable answer, sort of like my $10 per hour example. Most often what you'll do is plug in how many hours you work, and from that, get it back the pay that you're going to get from there. Given a table of values, we try to put the independent variable first. So that's my first big hint for grade 9, is that if you're having trouble deciding which one's independent and dependent, usually the one that's on the first column is the independent, and then the one that's in the second column is dependent. So if you're not sure which one's independent, go with this. Go with the independence in the first column and the dependence in the second. And when you're making a graph, we try to put independent along the bottom axis, along the horizontal axis, what we've been calling the x-axis, and we try to put dependent along the y-axis. Now, the homework and so on, your science classes will imply that it'll be obvious which one's independent and dependent, and that's not always true. We're just trying to give you simple examples in grade 9, and so usually it'll be fairly obvious which one's independent and dependent. If you do get confused, though, and you think, oh, well, either way, you could think of this either way, I totally agree with you. There's some examples like that. But we'll try to give you mostly examples in grade 9 where it's pretty obvious which one's independent and which one's dependent. Continuous and discrete. Before I even start the slide, I just want you to think about how we measure things. There are some things we measure with just whole numbers. For instance, if you counted the number of cars that went by your house, you would just count like 1, 2, 3, 4, 5. And when you just count things like that, we call it discrete. Now, if any decimal number or any fraction number is possible with the answer, then we call it continuous. It's a little deeper than that, but that's a great starting point. If you understand that part, you'll be okay with continuous and discrete for now. Maybe think about your refrigerator. If you went in the refrigerator and counted the number of apples in your fridge, you'd probably count them. You'd probably go, oh, there's 1, 2, 3, 4. If you're just counting things like that, it's discrete. However, if you were looking at the amount of milk in the milk container, there might be 300 milliliters, there might be 290 milliliters, there might be 290.4 milliliters. Any decimal is possible and a legitimate answer for amount of milk. So that's continuous. So that's the big difference. If you get that, you're home free and continuous and discrete. The rest of the slide tries to explain that a little more carefully. A set of data that can be broken into smaller and smaller parts and still have meaning, we'll call that continuous. Things like side lengths and volume can always be broken down into decimals. Time is another one that can always be broken down into decimals, and we call those things continuous. Discrete is a set of data that cannot be broken down into smaller and smaller parts. There's a limit to how far you can break this down. And the example talks about per minute billing on your cell phone. I want you to think about cars. Think about cars. You're not going to take a car and say, oh, 7.2 cars drove by my house. I mean, you can be ridiculous and say, oh, yeah, you can cut a car into smaller pieces. But that's not really how we count cars. And if you are counting cars that way, that's great. Then it would be continuous. I'll say most times when we're counting cars, we're counting them discretely. 1, 2, 3, 4, 5. And we're not breaking that down any more than that. We don't get any more carried away with continuous and discrete in grade 9 than that. Just a basic thought about what type of numbers we're using. Direct and partial variation. These are kind of important words because it tells you a little bit about what's going on with some equation or some relation. A direct relation is which one variable is just the multiple of another. So if you say Bill always makes 3 times as much as Frank, it's just one variable is just something times the other variable. And when that happens, what you get is an equation that isn't y equals mx plus b. It's just y equals mx because it goes right through the origin there down at 0, 0. That's what I really want you to think about, is that direct variation will go directly through the origin. Whereas partial variation is a relation that is a multiple of the other plus a constant amount. Those are a lot of what we've been talking about with linear relations. There's a multiple, mx, and then there's a b outside of that, something added onto it. So Gabby pays 0.25 per minute, or per gig, to put it into modern terms, plus a $16.95 monthly fee. You see, the graph of this relation will not start at 0 because it's not just a multiple, there's a multiple plus something else. It's enough in grade 9 again to go direct variation goes directly through the origin, partial variation starts partway up. So are these ones direct or partial? That one goes directly through the origin, so we call that direct variation. That one starts part way up the y-axis, so we call that partial variation. The table of values has 0, 0 on it. That's the origin, so this relation, if you graphed it, would go right through the origin, and so that would be direct variation. Y equals 2x plus 6. If you went to graph this, you would start at a y value of 6. You wouldn't start at the origin. You wouldn't start at 0, 0. So if you're going to start at 6, then you're starting partway up, and we call that partial variation. Y equals negative 8x. There's no y-intercept indicated there, which means the y-intercept, or the start value, is 0. And so this is just a graph going straight through the origin. This one's called direct variation. And finally, a word problem, a balloon starts at a height of 2. Well, I can stop right there. If it starts at a height of 2 meters, it doesn't start at the origin, and so this is going to be partial variation. The rate doesn't change my thinking at all as far as direct and partial. I just want to know where is it starting. That's what direct and partial is all about. Intercepts. Now, I've tried to introduce this in the other lesson so that this isn't a big shocker, but I'll explain it here like I haven't mentioned it at all. Intercepts are the value where the line crosses the axis. For instance, take a look at this graph of a line that we've got here. The x-intercept is the value where it crosses the x-axis, right here. There's the x-intercept. It meets the x-axis at an x value of 2. Notice at this x-intercept, the y value will be 0. That's the most important part of the page. So I'm just going to circle that. That's important. The y value is 0 at the x-intercept. For the y-intercept, the line crosses the y-axis. There it is there. Y value -4. And notice, this is, we've been calling this the start value or the initial value, but now we'll switch over. We'll start calling it the y-intercept, a slightly more powerful word. And notice that the x value here is 0. That's an important little detail that we're going to use in the next slide, and indeed in the next lesson. So, finding intercepts. A little introduction to it here, and then a big lesson on it next time. For each of the following line, determine the x-intercept and the y-intercept. On a graph, fairly easy. You just look for it and go, okay, where would the x-intercept be? You just look and see where it crosses the x-axis, right there at 4. Where is the y-intercept? Just look for where it crosses the y-intercept. There it is at 12. Okay, so what do we learn from this slide? Finding x and y intercepts on graphs, pretty straightforward. How about this one? Finding the x-intercept, well, it's sort of between two numbers there, so I'm going to have to sort of estimate it. Looks like about -5.5. Maybe you'd argue it was maybe -5.6, something like that. That's okay. When we have to estimate there, we'll give you a little leeway there. And for the y-intercept, well, it's between 10 and 12. I'll sort of say 11. It might be a little higher than that. When I look at it, it might be like 11.1, but close enough when we're graphing. Graphing's always going to be a little bit of an estimate. Now, finding intercepts from equations. This is the part that's a little more difficult, and so we dedicate a whole nother lesson to it, but I just want to introduce it here. If you want to find an intercept from an equation, we just need to remember that either the x value or the y value at the intercept will be 0. That gets a big box because I know what's coming in grade 10, 11, and 12, that sentence is going to come up a lot. Not that it's that difficult. It's not that big a deal, really, but it's important. So example. Let's say I've got a line that's y equals -5x plus 28. If I want the y-intercept, I just set the x value to 0. What I want to know is what y value will I get when the x value is 0. And so I plug in 0 and I get the answer 28. If you're right with me, you might think, well, I didn't have to do that. I knew just when I looked at the equation that that's the start value, that's the y-intercept right there. And I agree completely, absolutely. For linear equations, when they're in this form, reading the y-intercept off, you don't have to sub in 0. You can just read them off there. The subbing in 0 is for other situations where it's not exactly in that form. So we're getting you ready for other things here. So the y-intercept's 28 over here. X-intercept. For the x-intercept, we make the y value 0. So we put a 0 over on this side. And that gives you just a little bit more work to do because you've got to solve for the x. The way I did it in this particular one is I moved the 28 over, divided by the -5, and got an x-intercept of 5.6. So when you have to do x-intercepts, you might have a little more equation solving to do than when you do y-intercepts. Could we use the intercepts to draw the graph of a line? Absolutely. If we just graphed this point here that we got out of here, which is 0, 28, and we graph this x-intercept that we found over here, 5.6, 0, and just drew a line between those 2 points, that's another way to graph. And that's really what the next couple of lessons are going to talk about, is now we've got 2 ways to graph a line. We could use the y-intercept and the slope, or we could use the 2 intercepts. So lots of words in that lesson there to work through. Not too much of homework. You should be able to flip through the homework pretty quick. So a pretty light lesson today, but make sure you get through all that.